Okay, in lecture 24, we're going to be talking about the steady state and long-term behavior of a discrete Markov chain, discrete time Markov chain. So we've already done a little bit of this numerically in terms of talking about it looks like this example or that example went to what we called a steady state. And so in this lecture, it's not really a new concept, it's just formalizing the concept a little bit. Okay, so I said we have already seen this, so in lecture 15, if you go back and look at it, you probably remember this one. This was the one where we were talking about brand A ice cream and all the other ice creams out there, and that they did this advertising campaign, and you know who was going to buy what was the long-term aspects of having people buy brand A ice cream. So if you remember this, we had the two states. We had state A and A prime, which was everybody else other than brand A ice cream. We had our probability transition matrix, and remember if we actually went and calculated these out, we noticed that our states here on the right hand side started tending towards the same number. So here we had this was getting closer to 0.75 and 0.25. Notice it still gets closer. And then we said this was approaching steady state, so it was approaching this steady state. And we also did this example of what if we actually put in 0.75 and 0.25, then we multiply our probability transmission matrix by this, and we actually get the exact same thing. We get back out our initial value. Okay, so what we said previously was that the steady state then was an eigenvector corresponding to the eigenvalue 1. Okay, so this was our plot that we did from the plotstate.m file, and we noticed that it was approaching a steady state. Okay, so another example that we did was in lecture 16. It was the tea versus coffee people. And so we had a probability transition matrix P, which was this 0.7, 0.2, 0.3, 0.8. And here, notice what we had is that if we started with initial value, what our S1, S2, but eventually we start seeing that it starts leveling out. And when we plotted this, indeed our tea and our coffee was limiting on 80 and 120. So if we actually did this, plugged in 80 and 120, then we just got a straight line and stayed there for all time. So now what's that mean? Well, this gives us our long-term behavior. So in the previous example, we saw that if our initial distribution, our S0, was our steady state, then basically our Sn was always S0 for all time. So the notation, we're going to let pi j denote this long-term proportion of time that the chain spends in state j. So we're thinking about pi j as being our steady state. So we call our pi j our limiting or stationary or steady state distribution of the Markov chain. So remember what we have is we have the sum of our pi j's have to be equal to 1 because it has to be somewhere for all time. Okay, so if you have a positive recurrent Markov chain, then you have a unique stationary distribution. If it's null recurrent or transient, then there's no stationary distribution exists. Okay, so now how do we compute this long-term steady state? So we had an example. You can see it graphically, right? So we saw in our examples that you could see it was approaching a steady state. So how do we figure out, if it's not easy to just see from the graph, how do we figure out what this steady state is, what the stationary distribution is for this Markov chain? So here, we know that if it exists, that p pi has to be equal to pi in terms of if we multiply our stationary distribution by our probability transition matrix, it doesn't change, right? So p pi has to be equal to pi, where here the sum of all of these pi's has to be equal to 1. Okay, so let's look at an example of this. So let's assume we have state 0 and state 1, and this is our probability transition matrix. How do I find the stationary distribution for it without going and plotting all of this? Okay, so here I can set up my p pi equals pi. So here I have my p pi equals pi. Notice this is just like an identity matrix multiplied by this, right? So I can bring this over to the left-hand side and get zeros on this side. So if I subtract off the identity matrix from this, I have this matrix here left. So here I have a matrix. I have two unknowns and two equations. The thing is if I simplify this, right, it reduces down to really just one equation. So what I have is one equation. I have this minus 0.5 pi 0 plus 0.4 pi 1 has to be equal to 0. I can multiply by 10 and just make it a little bit nicer for myself. So I have now one equation essentially and two unknowns, but I need to also remember that I also have that the sum has to be equal to 1. So I actually have two equations and two unknowns. So here if I combine information from this equation and this equation, all of us know how to solve a linear system with two equations and two unknowns. So we can just simplify, and if we just simplify and get rid of the pi 0, so multiply this one by 5 here, and add it to this one, then the pi 0's go away and we get 9 pi 1 is equal to 5. Or pi 1 has to be 5/9, and then obviously if pi 1 is 5/9, then pi 0 has to be 4/9. So our steady state then is just 4/9 5/9. Okay, so another example is this example of a wildfire. So a Canadian forest fire weather index is used to estimate the risk of a wildfire, and the Ontario Ministry of Natural Resources uses it to classify each day's risk as nil, low, moderate, high, or extreme. So, so this person gathered daily fire risk data over 26 years at 15 stations and constructed a 5-state Markov chain model for the daily changes in the index. And so this is the model. So you have the probability of going from nil to nil, nil to low, nil to moderate, nil to high, nil to extreme. And this is kind of what you would expect, right? So if it's nil one day, the likelihood is it's going to be nil the other day, or it could possibly be low or moderate, but it's not likely that it's going to go from nil all the way to extreme. So anyway, this is a probability transition matrix. And so we want to know what the long-term, the steady state would be for this. So to find the steady state, we can use this p pi equals pi. So again, doing the same things we did before, we really have the identity matrix over here on this right-hand side, so we can subtract off the identity matrix, and we basically get this system. Okay, so remember we have this additional criteria that our sum of our pi j has to be equal to 1. Well, I don't know about you, but I really do not want to work with this system by hand. I mean, the 2x2 case was okay, not that difficult, but I don't want to do this by hand. So, well, we have MATLAB, we have other tools that can help us, so why don't we use it? So what I can do is I can add this additional criteria at the end of my matrix, right? So here I have the sum. If I multiply this out, I'm going to have pi 1 plus pi 2 all the way down to pi 5. The sum of those has to be equal to 1. So I just added on here. So I'm going to call this matrix something. I'm going to call it matp. And there's a nice command in MATLAB that if I put this matrix in and call it matp, then I can do RREF, which means reduced row echelon form. So remember from linear algebra, then you should know that if you have reduced row echelon form, it basically simplifies it. So now I can pick off my answers. This here is going to be my steady state. Okay, so this is going back to the example that we had before. This was our first example. This is our nice 2x2 case. We could easily compute our pi. We could get exact answers, 4/9 and 5/9. We didn't have to really estimate it over here in decimal form. But I'm going to show you another way of finding this long-term distribution, and it's using powers. So notice that if I take my P matrix and I square it, so look at what happens to my entries of my matrix. This column starts to get a little bit like this column. If I do this again, P cubed, notice my first column, my second column start to look a little bit alike. P to the fourth, because remember what we're doing, right? when you're figuring out what the next state is, then you're multiplying by p again. So to figure out what the next state is, I'm multiplying by p to the third, p to the fourth, p to the fifth. Notice here that my columns are getting about equal. If I do p to the 10th, my columns are exactly equal. And then just to make sure it doesn't change, I do p to the 20th, and yes, they're still equal. And furthermore, they're equal to what we got before, which is really good because then I can say they're equal columns. The column is our steady state. So everything is going to the steady state. So I really don't have to solve the p pi equals pi. This is another way that I can do it. I can do it either way and get the same answer. So using our wildfire example, using power, so remember this was our p matrix, this is what we found for steady state. So if I do this and I just take p to the 20 in MATLAB, so put this p matrix in MATLAB, take p to the 20th, and what do I do if I do p to the 20th? Notice that all my columns are the same, and they all equal my steady state here. Okay, so next time we're going to work on some examples.